deep learning based methods, particularly based on convolutional neural networks, and gained significant popularity by achieving state of the art results. So before moving forward, first let's have an overview of the convolutional neural networks. The basic and primary use of CNN or convolutional neural networks is image classification. CNN can be used for many tasks such as object detection and image segmentation, etc. You will use the shorter form of the convolutional neural network, that is CNN. A simple architecture of a CNN typically consists of convolutional layer, activation layer, pooling layer, and fully connected layer. The convolutional layer is the core building block of a CNN. It applies a set of learnable filters or kernels to the input image, which helps in detecting various features or patterns present in the image. Each filter performs a convolution operation by sliding over the input image and computing dot products between the filter weights and the corresponding image patches. Convolutional layer is responsible for capturing spatial hierarchies of visual features. The convolutional kernel or filter is applied over the image. Center element of the kernel is placed over the source pixel. The source pixel is then replaced with a weighted sum of itself and nearby pixels. After the convolutional layer, an activation function is applied element-wise to output feature maps. The activation function introduces non-linearity into the network, allowing it to learn complex relationship between features. Commonly used activation function include ReLU, which sets negative value to 0 and keeps positive values unchanged. In simple terms, the ReLU function takes an input value x. If x is positive, the ReLU function outputs x itself. If x is negative, the ReLU function outputs 0. This means that all negative values are mapped to 0, while positive values are left unchanged. Here you can see the ReLU rectified linear function is equal to maximum of 0 or x. So if the value of x is negative, it will return 0, otherwise it will return the 0 of x if the x value is positive. The pooling layer is used to downsample the spatial dimensions of the feature maps while retaining the important features. It reduces the spatial size of the representation, reducing the number of parameters and computational cost. The most common type of pooling is max pooling, where the maximum value in each local region is retained and others are discarded. For example, consider the max pooling on this image patch with 2x2 filters and stride 2. So here you can see the 2x2 filter window, and you will take the maximum value out of this window, and here you can see the 6, and stride is 2. It means you will move forward the window by shifting 2 columns, and the next filter window will be this one. So then again you choose the maximum value, and that is 8, here you can see, and so on. Pooling can be a max pooling or average pooling. In max pooling, you take the maximum value out of the filter window. Here you can see the maximum value in this window is 20, and here you can see 20, and 20 is over here in case of max pooling. And in case of average pooling, you take the average of all these elements in the filter window, and here you can see the average of these 4 elements is 13. So here you can see the simple CNN architecture. You give the input image and then convolutional layer and then max pooling layer, and then you can repeat many times these layers, convolution and max pooling, and you can use the activation function in between. So after applying the convolutional and max pooling, you flatten the output feature map, and then you fed to the fully connected layer of the network. The fully connected layer, also known as the dense layer, takes the flattened output from the previous layers and connects every neuron to every neuron in the next layer. It enables the network to learn complex combinations of features and make predictions based on them. The number of neurons in this layer depends on the specific task and the desired output dimension. So finally you will get the probability of the output classes. So after the fully connected layer, you apply the classification layer or softmax layers to get the probability of the predicted classes. So let's have an overview of the popular convolutional neural networks. LeNet CNN. The first successful applications of the convolutional neural networks were developed by Yan in 1990s. LeNet architecture was the best at that time to read zip codes and digits, etc. And then AlexNet convolutional neural network. The first work that popularized the convolutional neural networks in computer vision was the AlexNet, developed by the Alex and Geoff. The AlexNet was submitted to the ImageNet challenge in 2012 and significantly outperformed the second runner-up. The network had a very similar architecture to LeNet but was deeper, bigger, and featured convolutional layers stacked on top of each other. Here you can see the architecture of the AlexNet. There are 5 convolutional layers: convolution 1, convolution 2, convolution 3, convolution 4, and convolution 5. And in between the convolutional layer there is also max pooling. And at the end you can see the 3 fully connected layer: FC6, FC7, and FC8. Another popular CNN was a Google LeNet. The ILSVRS 2014 challenge winner was a CNN from Google. Its main contribution was the development of an inception module that dramatically reduced the number of parameters in the network as compared to the AlexNet. Additionally, this paper uses the average pooling instead of fully connected layers at the top of the convolutional net, eliminating a large amount of parameters that do not seem to matter much. There are also several follow-up versions to the Google LeNet. The runner-up in ILSVRC 2014 was the network from Karen and Andrew, that known as VGGNet. Its main contribution was in showing that the depth of the network is a critical component for good performance. Their final best network contained 16 convolutional fully connected layers and appealing features in extremely homogeneous architecture that only performs 3x3 convolutions and 2x2 pooling from the beginning to the end. Their pre-trained model is available for plug-and-play use in cafe. The downside of the VGGNet is that it is more expensive to evaluate and uses a lot more memory and parameters. Most of these parameters are in the first fully connected layer, and it was since found that these fully connected layers can be removed with no performance downgrade, significantly reducing the number of necessary parameters. The ResNet architecture is the most commonly used convolutional neural network. ResNet, also known as residual network, developed by Keming. It was a winner of ILSVRC Challenge 2015. It features special skip connections and a heavy use of batch normalization. ResNets are currently by far state-of-the-art convolutional neural networks models and are the default choice for using convolutional neural networks in practice. So here you can see the VGG16 architecture. There are convolutional layers and then pooling layer, and then there is a repetition of convolutional and pooling layers, and at the end there are fully connected layers, and then there is the architecture of GoogleNet. And here is the architecture of the most commonly used convolutional neural network, that is ResNet, with the skip connections. You can see the repetitions of the convolutional and max pooling layers, and here you can see the skip connections. So that was the brief overview of the convolutional neural networks. See you in the next lecture.